Good morning, everybody. Hope everyone had a nice weekend. Um, let's see what's going on. What did I do this weekend? So, pretty typical weekend. Let's see. Saturday, we hung out. Let's see. I did a bunch of schoolwork in the morning again. I wrote your acid base test this weekend, so that's written. Played some games. Went for a couple walks. It was a little chilly, so I didn't really get on my bike. Didn't do much of anything. I'm kind of getting tired of being stuck inside, I think, like all of you guys, too. All right, so kind of the plan for the week is we're going to do some notes today, and we don't have that much to do. And I'm going to give you tomorrow off, and then we're going to do notes, finish up the notes on Wednesday, and then we're going to take the test on Friday. All right, so that's kind of the plan for the week. And we're going to go from there. Now, before we get into notes, there are a couple challenge questions that we haven't gone over, so I wanted to quick run over those with you. So one from the 16th and one from Friday. So let's run through these. These are some things that you might see on the test. So number one, we have a solution that has a concentration of H3O plus. Now remember, that's the same thing as H plus. So there's my H plus concentration. So what is the concentration of OH minus and the pH of this solution? So this is two different problems, really. So let's start with the A part. And that is finding the concentration of OH minus. Okay, and we talked about, ooh, this pen is starting to die. Kw, okay, which is an ionization constant, all right, it's a constant of water, is equal to the concentration of H3O plus times the concentration of OH minus. Well, we have the concentration of H3O plus. Kw is a constant. It's 1.0 times 10 to the minus 14th equals 2.6 times 10 to the minus 9th molar times the concentration of OH minus. So our concentration of OH minus in this solution is equal to 3.8 times 10 to the minus 6th molar. So that's our OH minus concentration. The B part is to calculate our pH of this solution. So pH equals the negative log of the concentration of H3O plus. Well, we have this concentration, so pH equals the negative log of 2.6 times 10 to the minus 9th molar. So the concentration, or the pH of this solution, would be 8.59. Now, what does that tell us? Well, it's above 7, so this is slightly basic. So this would be a basic solution. And the concentration of H plus is less than the concentration of OH minus. And it is. Okay, if we compare our numbers, it is. All right. Let's try this. So this is a titration problem. Well, it's a bunch of stuff. So we do a titration with hydrochloric acid and the standard solution, which is calcium hydroxide. So hydrochloric acid is our analyte. That's what we're trying to figure out. And our calcium hydroxide is our titrant, or something called the standard solution. Okay, it's the one that you know everything about. So the first thing we have to do is we have to write this chemical equation. So hydrochloric acid, which is HCl, and it's an aqueous, plus calcium hydroxide, okay, and that's Ca, which is plus 2, OH, which is minus 1. So we get CaOH parentheses 2. That's also aqueous. Now, what type of reaction is this? This is neutralization. So whenever you have an acid and a base, it produces salt and water. This is just a special type of double replacement. So we crisscross the positive of the first, hydrogen, with the negative of the second, which is OH, and we get HOH. There's our water. And we have to do our salt, Ca and Cl. Ca is +2, Cl is -1. This comes over here, this comes over here, and we get CaCl2. Okay, now we need to balance. I think we need to put a 2 here and a 2 here, and I think that balances it. All right, so this is my acid. This is my base. It produces water and a salt. Okay, so there's my salt. All right. Calculate the concentration of the acid. Well, this is a titration problem, so we have MaVaICa equal to MbVbICb. So the molarity of the acid is what we're trying to find. The volume of our acid is 15.0 milliliters. Now, ionization constant is how many H's it's going to produce. How many H's is HCl going to produce? Well, remember, this is that 1-to-1 ratio. Right, so it's going to produce 1 H+, so its ionization constant is 1. The molarity of the base is 2.70 molar. The volume of our base was, what was the volume? 30.6 milliliters. Right, and our ionization constant of the base. So let's go to calcium hydroxide. How many OHs does it have? It has 2, so it's going to produce 2 OHs. Okay, it's a dihydroxy base, so its ionization constant is 2. Then we just do the math, multiply these together, divide it by 15, and we end up with 11 molar. Okay, 11 molar. This is a very concentrated hydrochloric acid solution. Right? If I ever gave you this, I would be in deep trouble. All right, now the last thing we have to do is we have to calculate the pH, which means we need the concentration of H+. Well, I want to show you something real quick. We know that HCl, when we put it in water, is going to break up into H+ and Cl-. So all of this is going to turn into this. So if this is 11.0 molar, okay, all of this is going to turn into this, so this is going to be 11.0 molar. So now I know the concentration of H+. Right, so once I know the concentration of H+, then we can go pH equals the negative log of the concentration of H+. pH equals the negative log of 11.0 molar. And when we do this pH, it turns out that we get a negative number, negative 1.0 for a pH. That's okay. There are actually negative pHs, and this is a perfect example. Okay, so when we have really strong acids like hydrochloric acid or nitric acid, and they're very concentrated, like this one is, they will have pHs less than 0. Okay, so you can have a negative pH. It's not very often. All right, now what is this really telling us? It's very, 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 very acidic. All right, and this is something that you wouldn't want to play with. Okay, all right, so there is our last couple challenge questions. I just want to get through those for you. Now, today, we really don't have, well, we have some work to do, but not a ton. But before we actually get into notes, there's a couple things that I kind of want to go over again, because I think students are struggling a little bit. So there are a few compounds that look like acids, that may look like acids or may not. They look like bases kind of thing. So there's some things I want to quick talk about. And these are really mostly our organics again. Organic compounds. So organic compounds are compounds with carbon in it. So there are a few of them I want to talk about, and we already talked about the organic acids, so let's just quick talk about those. Okay, organic acids are the ones that have that COOH usually in it. All right, cool groups. Okay, so something like C2H5COOH. This would be an acid, right? And this right here is the H that would come off. Okay, so we already talked about acids. And these are going to have pH less than 7. They're going to have a pH less than 7, right? Which means the concentration of H plus is going to be greater than the concentration of OH minus in these solutions. Now there's another organic that they're going to throw at you in this unit, and we haven't talked about them yet, but you need to understand them, and these are alcohols. And alcohols are carbon compounds with hydroxide polyatomic ions on them. Alcohols. So for example, CH3OH. Okay, so this is methanol. It's an organic compound. It's got carbon in it. All right, now this looks like a base. Why does it look like a base? Well, it's got this OH sitting right here. But it is not a base. Okay. It will not produce OH minus in solution. Okay, it looks like it does because it has this OH minus, but it won't come off. So if we look at, okay, we've drawn this and actually built this before. So this is methanol. Okay, so here's my OH group up here. Here's my OH group. Okay, this OH group will not come off the carbon though when we put it in water. All right, so it doesn't come off. It stays attached. So this doesn't produce any OH minus. It doesn't produce OH minus. If it does not produce OH minus, it doesn't produce H plus either. So alcohols will dissolve just like this, right? And they don't produce H pluses or OH minus. So what would the pH of an alcohol be? Well, if they don't produce OH minuses or H plus, the pH is going to be equal to 7. It's going to be neutral. Now, there's a couple ways that you're going to see alcohols. Here's another one. CH3, CH2, 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 OH. Right? This is an alcohol. It's an alcohol. It does not produce OH minus. Okay, its pH would be equal to 7. Okay, so you got all these carbons with an OH group on it. Now, let's see what I want to do next. One of the properties of acids and bases is that they are electrolytes, or they conduct electricity. Now I want to review this again. We've talked about it multiple times. How can a substance conduct electricity? Well, it can have free moving electrons. Right? These are our metallic solids, or our metals. Okay, free moving electrons. And the second way are free moving ions. So these are the only two ways we can have it will conduct electricity. So by looking at these different things, you have to decide, will they conduct electricity? Now, acids and bases, when they're dissolved in solution, produce ions that can move. So for example, HCl. HCl solid will not conduct electricity because it doesn't have any ions that can move. But if I put this in water and produce H plus aqueous and Cl minus aqueous, now I have free moving ions, so this will conduct electricity. NaOH, which is a base. NaOH solid will not conduct electricity. But if I put it in water, it breaks into Na plus aqueous and OH minus aqueous. Now I have ions that can move, so in the aqueous form, it will conduct electricity. Right? So now, you need to be able to look at a compound and decide, will it conduct electricity or not? Excuse me. So let's practice it. I'm going to give you some and we'll see if they conduct electricity. And why? How about Mg solid? Will that conduct electricity? And the answer is yes. Why? This is a metal. Metal have free moving electrons. Okay, they have electrons that can move throughout that matrix. If it's got free moving electrons, okay, it will conduct electricity. So magnesium solid will. How about HOH? Liquid. Pure water. Does pure water conduct electricity? The answer is no. Right? It doesn't have electrons that can move because they're stuck in place. And there are no ions. So this will not conduct electricity. Okay? Pure water does not conduct electricity. Tap water will. But why? It's the stuff in the water that's actually conducting the electricity. How about HNO3 solid? Okay, well, that's an acid, but it's in solid form, so these can't move, so this is a no. But what if I do this? HNO3 aqueous. Now I've dissolved that in water, and I get H pluses and NO3 minuses. This will conduct electricity. How about CH3, CH2, CH2OH, aqueous. What if I put that in water? Will that conduct electricity? Well, what is it? It's not a base, it's an alcohol. All right, so this is an alcohol. Remember, alcohols don't break up in water. It doesn't form OH minus. It's not going to produce ions, so this will not produce electricity. It will not conduct electricity. How about KBr solid? Well, that's a salt. Do salts conduct electricity? Not in solid form, they don't. So this is no. But if I have KBr aqueous, it will, because it produces ions in solution. How about this one? CH3, CH2, CH2, COOH. Will that conduct electricity in aqueous form? Well, what is it? Now, as soon as you see this cool group, you know that it's an organic acid. Acids in aqueous solutions will conduct electricity, so this is a yes. Let's see. How about C6, H12O6 aqueous. In other words, we're dissolving glucose in water. Will that conduct electricity? Well, glucose is a molecular substance. It will not break up into ions. This will not conduct electricity. How about this one? CH3, CHOH, CH2, CH3. I'll kind of move things around a little bit, but what do you see in there? Okay, we have all these carbons with this OH group in here. Well, this is an alcohol. Let's make it an aqueous. It's an alcohol. Do alcohols break up into ions? No. So this will not. All right, so this is something you need to be able to do. You have to identify what type of substance it is and decide if it will conduct electricity or not. All right, so I just kind of wanted to run through this with you. All right, again, all right, this is an important idea. And we've done a lot with this year. All right, so we're going to get into our next theory. Of acids and bases. So we've been dealing with what's called the Arrhenius theory of acids and bases. And Arrhenius defined an acid as something that produces H pluses in water. And he defined a base as it produces OH minuses in solution. Excuse me. There are other theories of acids and bases, and those are the ones that we're going to look at one of them today. And this is called Bronsted-Lowry theory. There are actually notes over that. Bronsted-Lowry theory of acids and bases. Now, Bronsted-Lowry, these two people didn't say Arrhenius was wrong. Okay. All they did is they said, hey, look, there are other substances that act like acids and bases that Arrhenius can't account for. So they said, hey, Arrhenius is right, but there are other substances that react as acids and bases. So they added to the Arrhenius theory. Okay, so this theory extends the Arrhenius theory. And Bronsted-Lowry define an acid is any substance that donates a proton. Remember, a proton is an H plus ion. Any substance that donates a proton to another substance. Any substance that donates a proton to another substance. These are called proton donors. Now, this is really just like Arrhenius. Okay, there isn't much difference between an Arrhenius acid and a Bronsted-Lowry acid. The biggest difference is in the base. A Bronsted-Lowry base is any substance that accepts a proton from another substance. And these are called proton acceptors. Nowhere does it say anything about OH minus in here. Okay, so we have proton donors, which are acids, and proton acceptors, which are bases. Now, let's look at a couple things. HCl plus HOH. Okay, so we're putting acid in water. It goes to H3O plus and Cl minus. Okay, so now let's look at what's happening. Okay. How did this H3O plus form? Well, this H right here was donated by this substance to this water molecule over here. So this is a proton donor. Okay, what was the water doing? Well, it accepted that proton, so this was a proton acceptor. So in this equation, the HCl acted like a Bronsted-Lowry acid, and the water is acting like a Bronsted-Lowry base. Now, in this substance, this is what gives us our acidic properties. All right, well, let's look at a different one. Let's look at ammonia, NH3. NH3, and we're going to react it or put it in water again, just for fun. And what happens here is this H right here is donated to this guy over here. And we end up with NH4 plus and OH minus. Now, this is acting as a proton acceptor. The water is acting as a proton donor. So the ammonia right here is acting as a base, and the water is acting as a Bronsted-Lowry acid. Now, I want you to look at something real quick. In this equation right here, the water was acting like a base. In this equation down here, the water was acting like an acid. There are a few substances that can act both as a proton donor and a proton acceptor, and water is one of them. And those substances have a special name. They're called amphiprotic substances. Sometimes they're called amphoteric substances. Same thing. Amphiprotic, amphoteric substances. These are substances that can act both as a proton donor and proton acceptor. Okay. Amphiprotic or amphoteric substances. All right, so these are substances that can act both as an acid or a base. H2O is an example. All right. Good. Now I want to go back and I want to look at these again. All right. Anne Bronsted-Lowry theory. Okay. If there is an acid in the equation, there also has to be a base. Okay, because in Bronsted-Lowry, something is donating a proton and something else has to be accepting that proton. So in Bronsted-Lowry theory, there is always an acid and a base in the equation. So let's go ahead and write that. So according to Bronsted-Lowry, theory, every equation that has an acid must also have a base. Okay. If we have something that is a proton donor, that means we must have a proton acceptor. So let's look at another one. Let's say we have ammonia, NH3, plus, how about HBr? So we have ammonia and we have HBr. Well, this is a base and this is an acid, but why? Well, in this equation, this H right here is going to be donated to the NH3. So we end up with NH4 plus and Br minus. So the NH3 is acting as a proton acceptor, which is a base. In Bronsted-Lowry, we have to have both. So this is acting as a proton donor, which is an acid. All right. So we're going to start one last little thing, and these are called acid. This is some acid-base equilibria stuff. All right, and it's based on Bronsted-Lowry. And then we're going to stop. And we'll finish this up on Wednesday. Acid-base equilibria. So we've already talked about equilibrium. Okay, and remember at equilibrium, the rate of the forward reaction is equal to the rate of the reverse. Well, acid-base equations actually are equilibrium equations. Okay, so these are equilibrium systems. So let's look at this. Let's say we have HNO2 plus HOH. This is going to form an equilibrium. And it's going to form H3O plus and NO2 minus. So if we look at this in the forward direction, so if we're going to look at it in the forward direction, this way, HNO2 is going to donate an H plus to HOH and produce H3O plus and NO2 minus. So what happens is we're donating a proton. So this is acting as an acid in the forward, and this is acting as a base in the forward. Let's look at the reverse. In the reverse reaction, NO2 is accepting a proton from the H3O plus to produce HNO2 and HOH. So in this case, this is acting as a base, and now this is acting as an acid in the reverse reaction. Right, so now let's look at here. What does this turn into? HNO2 turns into a base on the other side. So the acid on the left turns into the base on the right. Well, what does the HOH do? It's a base on the left, and it turns into an acid on the right. Okay, these are called acid-base pairs. So the acid on the left, becomes the base on the right. And the base on the left becomes the acid on the right. These are called conjugate acid base pairs. They're called conjugate acid base pairs. Now, you need to be able to come up with an acid conjugate base and a base conjugate acid, and it's really easy to do. Okay, it's really easy to do. So let's go over here. So let's just label this conjugate acid base pairs. All right, and we're going to start with an acid going to its conjugate base. All right, so in our example a second ago, we had, what do we have? HNO2. We had HNO2. Okay, that was the acid, and it went to NO2 minus. So what happened is we went from the acid to the base. Well, it will lose one H plus ion. That's what's going to happen when we go from the acid to the base. It loses an H. Okay, so let's say we have HCl. What would its conjugate base be? Its conjugate base would be one less hydrogen, so it would be Cl minus. That's what its conjugate base would be. Let's say we have H2SO4. What's its conjugate base? Well, it's going to lose one of those hydrogens. So it would be HSO4 minus. What if we had HOH? If this is acting like an acid, its conjugate base, it's going to lose one of those H's. So its conjugate base in the equation would be OH minus. Well, that kind of makes sense. All right, well, what if I give you a base and I want the conjugate acid? Well, let's look at what our example did. So in our example, we started with HOH. It accepted a proton and became H3O plus. Okay, so in this case, we're adding an H plus to whatever this is. Right, so when we're going from a base to a conjugate acid, it's going to gain one H plus ion, which is exactly what this did. All right, well, let's look at some of these. How about NH3? if that's its base, its conjugate acid is going to have one more H plus ion, so this becomes NH4 plus. It gains a hydrogen ion. How about we have, let's say we have Br minus, and that acts like a base. Okay, its conjugate acid, we have to add a hydrogen, would be HBr. How about, what if we had NO3 minus 1? If that's acting like a base, its conjugate acid would be, we have to add an H, HNO3. What if we had, how about if we had HSO4 minus 1? If that was acting like a base, its conjugate acid would be H2SO4. Now, you need to recognize conjugate acid-base pairs. You should be able to look at an equation and tell me what the acid-base pairs are. And you should be able to, if I give you an acid, you should be able to give me its conjugate base. And if I give you the base, you should be able to give me the conjugate acid. Okay. We're going to expand on this tomorrow, or not tomorrow, but next class. All right, so we're going to stop here. All right. This is the end of the lecture for today, and we will finish up the notes on next class. All right, hope you have a good afternoon, and we'll see you soon. Talk to you later.